So we'll be talking about connectivity. So what is connected? Connected, so we introduced already paths in the last class. So basically a graph G is connected if for all pair of vertices there exists a path. So if I would have been teaching somewhere else, I would have said, hey, is this graph connected? Is this graph connected? Is this graph connected? No. Is this the whole graph connected? Very good. So at least now all of you know the definition of connectivity, I'm quite sure. Okay. So the first theorem that I would like to prove, okay, then also, you know, like we say that, oh, graph induced on U is connected, meaning, right, which basically means that if you look at the think of this graph induced on U, it also introduces a graph, right, and that graph has this property. But by connectivity, you mean the path here. It's not that the path is from outside. Okay, you get my point, right? So when you say graph U is connected, it means that two vertices have path between them in graph induced on U. Okay, in this small portion, right? Not here, nothing like that. Okay, so that's one thing which is very clear. U with some vertex of subset VC. So the first theorem that I would like to prove is that, okay, let's see if we can, this is a very useful theorem I find. Okay, let G be a connected graph. Okay, so G is a connected graph. Okay, then vertices of G can always be enumerated say V1, V2, Vn, so that Gi, which is basically graph induced on first I vertices, is connected. Is connected for all. Okay. So what does this tell? If a graph is connected, then we can come up with an enumeration of vertices such that if I look at any top I vertices, first I vertices, the graph is connected. And like for that matter, any, like if you look at any prefix of this with this enumeration, that is connected. Okay. Now, not any will help you. For example, look at this. Right? Look at this curve, right? And suppose I have A, B, C, D, right? If I write B, C, A, D, graph induced on B is connected because it's a single vertex. But is the graph induced on BC is connected? No. So this enumeration is definitely not a valid enumeration for this. Right? So what should be the valid enumeration? So you understand my point? That not every enumeration of vertices would satisfy this property. But if the graph is connected, there exists an enumeration which satisfies this property. And why it is an important thing to have? Because whenever you are trying to do some sort of induction and you wanted to maintain a connectivity property at every process, right? Then this is the right way. Okay, so fix this enumeration and we are going to do induction or whatever on this sequence. Okay, so we can assume this and that will help us do some things as we go along. Okay, but now, so what is that kind of enumeration that you could think of? Suppose we have partially constructed some, The best way to view it. Suppose I have partially constructed our prefix. Okay, so this is a partially constructed prefix, and it has the property that you desire. That if I look at any prefix of this, it has a property. Now the next question is, what should be the next vertex? Right? What should be the next vertex? What do you think could be the right choice for this vertex? You get my question? Why such vertex exists? What? Which edge? Suppose this is edge. Okay, now what are you saying? You take a vertex x, okay, with an edge. Prove such a vertex exists, no? So you're saying there exists a vertex, x such that there exists y in edge such that xy is in G.
Can't we do a DFS start with some arbitrary vertex and then enumerate all the vertices level by level from left to right?
Who is saying this? Huh?
Right and zero.
Okay. No, I have not used the word BFS, DFS yet, so you can't use it. All you can use it some degree and connectivity definition. And even then, that's not correct. I can prove to you. I take BFS layer by layer, take this. When I'm enumerating the vertices of the same layer, I'm dead. I'll give you an example. Okay. Right? Okay. Or maybe not, let's say. What is saying? No, this is fine because if you do anything, their neighbor is here. So that's fine. Okay. But no BFS. We don't know this BFS, DFS yet. We have not talked about trees in the class. No, I'm saying that you can argue about existence of such an edge. Please argue. Intuition is fine. I want a proper one line. Not enough. Not enough. Here is the definition. Here is your definition of connectivity. This is all that I know. You need to build an argument starting from here. Yes.
So remaining vertices create a connected graph and you can try to find
Other outside may not be connected at all. G minus H may not be connected at all. I have no clue. Yeah, so pick up any vertex which is outside edge. Okay, so think, here is my edge. Okay, all I'm trying to tell you, teach you, be disciplined to use whatever it is. It's like a chess game. You can't make your own rules. Here the rules are fixed. When I say rules are fixed, let's try to use the knowledge which we are building over the period of time. Right? Then you will see the beauty of why it is. Right? Okay. So now there is an edge. Okay. And suppose this is not whole of the vertex set. It means there does exist a vertex which is outside. This is guaranteed to me. Now, what do I know? The whole graph was connected. This much I know, right? If the whole graph was connected, then there exists a path from a vertex. Fix any vertex here, say y. Okay, let's X here and Y here. So because my graph G is connected, there exists a path starting from X to Y. Do you agree? This is an important argument that we must see once for all. Okay. Now that path, okay, how does that path go? This is how this path could look like. Okay. So what is the right choice for vertex in this path? First vertex. You get my point? Right? So this is a path, or I could say so either I can say I start from X, okay, I start from X, okay. Look at the first time I leave X, like leave the vertex at H, right? And I have to leave because Y is outside, okay. So all I'm trying to say that these are the kind of arguments that you need to learn. That I have a structure inside and there's an outside, okay, and I'm trying to construct a path which is going from inside to outside. So what I want you to teach is this inside to outside argument. Okay, this is an argument which you will be able to use in different situations, right? So whenever you have a connectivity and some such thing, it is the inside and outside argument which is used all the time. Okay, so what will be, okay, let Z be the first vertex outside H while traversing the path P starting at X, right? Now this is a path, right? What is this vertex? Z. By choice, Z is outside. And why such Z exists? Because Y is outside. Otherwise, so you understand? You have to ask why such a Z exists first of all, right? Because we know such a Y exists, right? So at least the end point. So even if I'm traversing, at least Y will be that vertex which will satisfy this property. Okay, but Y is the first vertex when we leave this. Then where is its predecessor? Predecessor is this. And where is this? It's inside H, right? So now I have found a vertex, right? Inside H, one outside, and that has an edge. So this property is actually true. Then we need to prove it, right? So, I mean, and now all of you are right. Put that Z, okay, in this place. Make it. The graph remains connected, and again the graph G is connected. I can do this, okay? So I can either apply induction or some such process to make the proof form. But what is an idea of inductive argument is that given at any point of time a GI which is connected and a vertex outside, because my graph G is connected, there exists a path, what do you call, joining a vertex inside to outside. Now on that path, pick up a first vertex which is leaving this, and that is your choice. And that's it. Okay, so that's fine, right? So this is what I mean by using only things which we are made. Of course, once we have, there are several proofs. Like if I tell you by BFS, DFS, that's obvious. Like why only layer by layer? If you want to see more clearly, there is a more trivial proof which is extremely useful if I really want to. What? Look at a graph G. Okay, but again now I'm using facts. Okay, so if G's graph is connected, there is a spanning tree, right? Agreed, spanning tree, right? Fix a leaf, delete it. Is the remaining graph connected? Okay, so now you make in the reverse this sequence. I took out the leaf, the remaining graph is connected. Now in this tree, delete a vertex, delete it, right? Another leaf. Do this leaf deletion, right? This is your connectivity sequence. What do you mean? Look, I delete a vertex, which is a leaf. Graph is connected because this is connected. I have an example why it is connected, right? Okay. Now it's prefix, right? So I have to make them connected like this, not like this. I'm making the sequence in the reverse order, not in the forward order. This is exactly what I'm saying, right? So leaf is here. What is a witness? That everything before is connected because this spanning tree is connected. So here's a, okay. Now in this tree, I take out a leaf. What do I need witness? That remaining is connected. This spanning tree anyway. It's connected. So on and so forth. Now, once I have made this sequence, now you go forward and check that this property holds. That every prefix of this sequence is connected. Right? So there are several proofs, but like, or as he says, take BFS tree, take layer by layer. Perfectly. But why this is useful? Again, when you try to do induction. Right? I want to delete vertex so that the property is satisfied. So I will delete this vertex as the property is satisfied. Okay. Okay. Yes. That's a good question. Mm, it could be more. I'll tell you why. Look at any spanning tree. Fix a spanning tree. That itself can give you many such enumeration based on which leaf I start with, for example, as my last, right? So if it has 50 leaves, for the last vertex, I have 50 choices, right? For the second guy, the number of leaves I can create, that many choices I have, right? So even for one particular spanning tree, we could create many such permutations or sequences. So I don't think they are bijective corresponding to each other. But or this sounds a bit okay. I don't know. But yes, yeah. So here's a question for you: how many of them are there? Characterize that, or come up with some generating functions and all. Give a right, give a asymptotically tight bounds. That's a question. I'm not doing those. I just don't know those. Okay, but yes, these are very valid questions. No? Another question, forget. So these are like graph theoretical or combinatorial question. What will be the algorithmic question? How many such are there? Can you find it in polytype? Can you count such, like can you count this number of sequences in polynomial type? Or this is SAR P hard? If it is SAR P hard, can you come with still a good algorithms? Right? What is a trivial algorithm for this? What is a trivial algorithm for this? Yes, I can enumerate all n factorial permutations because that is all that, and I can check which of them are satisfied. So the number of such objects are upper bounded by n factorial. So this, but can I do much better than n factorial? And it looks like that we can. If you follow that permutation, we can look like we just talked about it just now. Okay, but what is it, right? But in polytime, I don't know. Maybe it is RP. It's a good question to ask. SAR P hard. You're doing a complexity course now, huh? You will learn. It's a counting version of polynomial time, right? So in polynomial time, we only talk about decision version. Now we say how many such objects are there? Is the number, say for example, how many maximum matchings are there? How many perfect matchings are there? These are the kind of questions. So we ask counting questions, right? So the most classical is permanent is SAR P hard, right? Which gives you that counting matchings are SAR. Look, finding a maximum matching is polytime, but counting number of maximum matching is not hard. Like you can't do that in polytime. So for counting problems, we need a different world of theory, and that is what is provided by SAR. So you should be doing this in your complexity theory course. Okay, right? Otherwise, how will we show that the computational question is not easy, right? So we need some methodology, right? So that is the methodology provided by. Okay, okay, uh, okay. So now I'm going to introduce terms like separations and this and that because Okay, so what I'm going to do now, okay, is the defining the terms like separation. Okay. So what is the separation? So you're given A comma B subset of V, and now you're given X, okay, which is again subset of V union B. Okay, so it's a very general form of separation. And what is the, but A and B are vertex set. What is the property that in G minus X, like you delete the vertices which is in X as well as delete the edges which are in E. Okay. What is the property? There is no path from a vertex in A to a vertex in B. So after I delete these things, A gets separated from B, right? You get my point? So after I delete this, there is no path from a vertex in A to a vertex in B. But now let's ask us a question. In my definition, I have never said that A and B are disjoint. I just said A and B could be any vertex. So what do you think about A intersection B? Okay, so rather I should say there is no path from a vertex in say A minus X to vertex in B. So you could delete some. Okay. Now, so where do you think A intersection B lie?
Subset of X.
Correct. Okay. So this is a and there's a common terminology which says X separates A and B, like two vertex A and B, if in G minus X there is no path between A and B, and of course A and B is not part of X, right? So if I give you A and B, X is separated. Okay, these two vertices. Suppose if A comma B has an edge, can you separate it in this definition? Can you separate a pair of vertex A and B if they had an edge? Correct. But if I allowed only X equal to vertex set, then we can't, right? If X was only allowed to contain vertices, then you can't disconnect a pair of vertex A and B if they have an edge. Okay, so some simple things to remember. Okay, so they have a term. Okay, so if X is only part of V, they are called separators. Okay, or vertex separators. Okay, and of course, if X is only contained in E, we don't just call it separator, we give it a name. It's separator. Okay. So now what theorem do I want to prove? Okay. A common terminology that is used, and this is the most, okay, we say A comma B is a separation of G. Okay, so A comma B is a separation of G if the following properties are satisfied. First, A union B is the whole vertex set. That's the first property. Secondly, A minus B, what do you call? No edge between A minus B and B minus C. there is no edge between A minus B and B minus A, right? So basically think of this, right? And what is A intersection B? This is called order of separation. So from the first lecture itself, I'm defining this notation so that I can follow it throughout. So this is the most common used literature, that what is a separation of A comma B is a separation of G if A intersection B is VG and A minus B, and there is no edge between A minus B and B minus A. And what is A intersection B? This is called order of separation. Okay, so we are only talking with respect to vertex separation. Okay, so for example, suppose I have a component and component. The way you would have looked at in your literature or book is that, oh, this is my separator, separates this and this. Now, how can I form a separation, ordered separation? You just take A as this and take B as this. So now red part is the common part between these two, so it becomes a separation. And this is called order of separation, meaning how many vertices do I need to separate something? Okay, is that fine? Yes. So graph induced on A could have an edge. Yes. No, but I do not understand what your question is. Yes, I just said. Vertex sets, because A and B are subset of VG. So I write A and B equal to VG. Right? So can they contain edge? No. A and B is just a partition of, like, I shouldn't call, they are two subsets of my vertex set. If I take their union, it is equal to my whole set. And if I take their intersection, there is no edge from this side to that side.
So when we say A, B is a separation of G,
If these two properties are satisfied.
I have one doubt. So AB is not disjoint.
No. Of course, otherwise, what is the point of intersection? This is an important point, that they are not disjoint. Okay. Lot of people also write A, X, B. That's just not good notation. Like A, X, B. After I delete X, there are no edge between A and B. I don't know. This is This is a very clumsy notation, which when I have to define minors and tangles and like all this will become hell. So preparation from beginning, we set ourselves this. So okay. Now there are several things which I must have heard. K connected, okay. K edge connected. You've heard this word? Graph is K connected. What is the meaning of graph is K connected? Okay. So tell me, a graph G is, you're right, is K connected if first of all, this is K doesn't equal to K, otherwise it doesn't make any sense. Okay. And G minus X is connected for all X mod X less than equal to K. So you can't disconnect this graph by deleting, say, at most K minus 1 vertices. Then this graph is called K connected. Okay. So graph G is K connected if the minimum number of vertices we need to delete such that graph has at least two connected components is at least K. Okay. Okay. So what are one connected graph? Every connected graph is one connected because you at least need to delete one vertex to make it disconnected. Right? Okay, so let me see if you can. Let's see. What is the connectivity of this graph? Can I delete one vertex and make this graph disconnected? No, right? We at least need to delete two vertices such that the graph contains two connected components. Okay. What about this? Yeah, so if you just delete the center vertex, and unfortunately or fortunately, I mean, these vertices has a name. They are called cut vertices. Okay, they are called cut vertices. So now the way we have k connected definition in the realm of vertex, we also have definition in the realm of edge connectivity, right? So same thing, but we'll prove a nice theorem in a minute. We will have this kind of definition galore only till tomorrow. After that, we will have one definition and a month. Okay, so just bear. What? Zero connected? I don't need to delete anything. Have you people attended any lecture in this recently organized RTA? No, recent advances in this. So, for which of this problem we had a 2-hour lecture? I just want you to feel. Wait. You understand what I'm saying? Was it a vertex or edge? Right? So we spend. So all I want to tell you, the first thing which you are learning in your graph theory course, for which we are still trying to find the best algorithms, right? And hot topic algorithms. Okay. So just to relate to you, right? This is why we should be attending these kind of workshops, because at some point of time we can connect whatever we have seen there to this, and if that brings some curiosity, we just go back and try to relook those. Okay? This is why, I mean, maybe some of the most things which you hear in the beginning of your some of these talks, trust me, you will understand very little. But with time, you start to connect these things very, very differently. Like, and thirdly, don't compartmentalize yourself that I do algorithms, I do logic, I do theory of computation. At a larger level, they all are interrelated to each other, and you can find some good tools from here to use here, some great tools from here to use here. Okay. So, for example, in logic, or all these verifications and all this, they did not have tools for a long time to. So, all they showed is certain kind of hardness, like exp space, p space, like not computable, and this. Okay. So, those are great results theoretically. But now, because of parameterized complexity, they started to say that, look, the kind of things which we are dealing with, for which we are showing this lower bounds, are very, like, we are creating those instances. You understand my point? Like, these are like hardness based instances, but those are not what is coming in the verification in the software or this and that. So, what are those parameters that is actually doing it? So, for example, you look at any database and you want to search query. Do you really search query of length more than 10, 20? Think about it. If you have a database, do you really search a query of more than 10? Right? But searching this query in a big database is a very, very hard problem. Right? But there is an algorithm which runs in time 2 to the power size of the query times linear in the database. But 2 power 10 is nothing, right? For the modern computer. You understand how efficient? So all I'm trying to tell you that you get questions from all over the places, and whatever knowledge that you have gained, you can apply some of those to learn those things. Okay. Okay. So my initial motivation to do algorithms came from graph theory when we were doing discrete maths, because some of these questions look, but how do you do this? For example, my personal motivation was that there's a proof in graph theory about this characterization for Eulerian graphs, that every vertex should have even degree, okay, a connected and even degree. Now, that is a course which I did in my second semester, so I have not been introduced to algorithm that, but it is like someone told me that it's poly time, and someone I knew somehow that people have been talking in some talks and this, that Hamiltonian cycle is NP complete, but this is poly time. But it doesn't look like that it is also a traversal of edges, right? Because vertices can, but edges do not repeat, right? Why there is, like, you understand the, right? So it, like something which I kept in for a long time, and for us the next semester was followed by an algorithm course. So I remember going to Venkatesh and saying, like, in very first second lectures, talking about this, and then he said, oh, no, wait, you will learn, you will see. And of course you build but like this curiosity that like something is very hard. So I was also following this book by, for discrete maths, what is this person, great name, huh? No, he died recently. He's a not Hungarian, he's a Czech Republic person, I forgot. Huh? Not, huh? Yes, right. So he deals his graph theory book or discrete math book with an algorithmic perspective. So he will ask you some of these questions. So this is how we learned. You get my point? So like, so from there, so this is why for me when I do graph theory, I also need to understand what are the computational question one can ask. I'm not going to deal in this course because this is all about structure, but at least to be aware that these are the right set of computational question one can ask. And at least if you find something interesting, go check on the link. I'm not saying go, like, at least Google it. Okay. So why I brought this up? Because look at this. Look at the edge version of this question. What is an edge version of this question? Right? So we'll say a graph G is K edge connected if I think the number of edges should be more than K, right? So I think, let's say L connected, L edge connected, if cardinality of G is more and G minus F is connected for every F subset of E and same definition, right? Now, minimum K for which a graph is K connected is denoted by, I think, denoted by kappa of G. Okay, unfortunately, uh, okay, K of G. I can't denote this very well. Okay. And for which L, for which a graph is L edge connected is denoted by, I think, lambda G. Yeah, lambda G. Okay, that's it. Now, what is the global min cut problem? Is finding this lambda G. Global min cut is finding lambda G. So, hopefully, we will have an opportunity to see this contraction algorithm of Kargar, which is like benchmark all over the place. And then, hopefully, if someone is interested to learn how the isolating cut and these kind of algorithms works with small number, right? So this can be computed using some n-1 max flows, but he said that we can also do it in polylog max flows, right? How to do this, right? Using this. So the problem is this. So like, if you look at the, like, one can just do a master thesis or something by just learning algorithms for this problem. There is so much literature on this. Okay, but beside this point, but now I want to prove a nice theorem. What is a nice theorem? We have done too much of definition. Any question?
Sir, I have a question.
Please ask.
In place in the vertex,
What?
minimum, I think it should be maximum.
Right, you are right. You are 100% correct. It should be maximum k for which a graph G. Thanks. Thanks for pointing it out. Okay, it shouldn't be minimum. It's a maximum k for which this property holds. Because if it is minimum and the graph is connected, take 0. Right? Is right. Okay. So the proposition which I want to prove that if a graph G is non-trivial, which means it has at least one vertex, okay, then the following property holds. Kappa G is less than equal to lambda G, which is less than equal to minimum degree. Yes, this is what I want to show. Okay, so this is a theorem which I want to prove in next 10 minutes. Okay, so I'm going to keep this definition and trying to use this part. Okay, so tell me which of these inequalities is easy to show. Which one of these inequalities is easy to show? Huh? What? Hmm. Absolutely no. Think about it. Not true. Absolutely not true. I mean, of course this is true. Or like the way you are saying, okay. Yeah, so what he's saying is that, okay, so let's see if single vertex, what is the connectivity of single vertex? Yeah, it becomes 0. Yeah, fine. Like, what is the definition of, let's say, okay, fine. But is this not easy to show by the same argument? So what I'm trying to tell you that look at any vertex, and look at the edges which are incident on this, right? It's a non-trivial graph, right? So if I delete all these edges, incident to V, I can definitely separate V from every other vertex, right? So what is my best bet? You pick up a vertex V with minimum degree and you delete this, right? So as Sanjay was saying, he was trying to say for vertex, but like, let's do it for edges, like we can prove something much. So this implies that lambda G is less than equal to delta. And this inequality is the crux of many good algorithms for global mankind. It's simple. I'm not saying it's very difficult, but like, okay. But what about this? Now you have to show that kappa G is less than equal to lambda G. It sounds very intuitively correct, no? Right? You realize what I'm saying? Does it not sound very intuitively correct that this should be true? Because a vertex has way more power to delete, because when you delete a vertex, you delete all the edges that are adjacent to this vertex or that are incident to this vertices, right? But when you delete an edge, you can just delete it. So shouldn't you come up with some strategy, or at least tell me something which you feel could just work? You understand my question, right? Look, when I delete an edge, I just delete an edge. But when I delete a vertex, I not only delete him, I delete every vertex that are incident to that. Right? So if this inequality seems very natural, but how do you make it formal? Look, in the beginning, I'm just trying to be slow and give you time to think so that when we are talking about slightly more complicated thing, we are at the same page. That's your choice. That's entirely your choice, right? Which, look, for our proof, it is, look, we have to show this is this. So I could start with, so let's write down, let, no, I shouldn't do green because it's not visible. Let F be subset of EG, and what is the cardinality of F? Is lambda G. How does the world look like? Because now we are deleting edges, right? So we will have some components all across the places, and these edges flying around here, maybe here, right? This is how F is. So if I look at this, do I have a choice of which vertex to pick? Imagine, let me give you a situation. Okay, suppose I have a vertex V here with a property V is not adjacent to any edge in F. There is some vertex V in some component. How is the property? He is not adjacent to this black edges. He is not. Can you come with some strategy now? Pick one vertex, each, which edge? We don't have to worry about everything else. We can just pick edge. Suppose this is a component C. We can just pick edges incident to F with component C, right? These edges, vertices. Why? Because V is not adjacent to this. So when I delete this, V will be here. But now V will be separate because it's a non-trivial thing, right? So F are going, look, no incident, no, F is not, no edge is contained inside C because how did I draw? It's a component after we delete this edge. So all the, right? So there will be a V here and there will be some other vertex. So if there exists a V which is not adjacent to any F edges, then we think we have a strategy to find such a separation. And look, what is the property of this separation? You have only deleted one vertex from each of F edges. So definitely this separator size is less than F. Because look, we have a separator, but we need to upper bound the size of the separator from cardinality of F. You get my point? Because that is what we are trying to show. Okay. So two things to notice. So what are the two things to notice? First, suppose there exists a vertex V not adjacent to any edge in F. Okay, and then let C be the component, connected component of G minus F containing V. Okay, right? It can be adjacent. It can be. I've never said. I say suppose. We'll get there. We will get there, right? Or I'm trying to like create a situation which at least we can handle. So I'm saying to you that if there exists a vertex which is not adjacent to any edge in F, then I actually know how to handle what I said. Then let's see with the connected component of G minor containing V. Then, okay, then C intersection VF, okay, is a separator of size at most cardinality of F, separating V from at least some other vertex. Okay, right? Because you got at least two connected components. That is the property of this. So now you, after you deleted this, there's some other vertex, right? In some other component, right? That survives. So that vertex and this vertex got separated. It's important. You get my point? Okay. But now, maybe this is not the case. For every component, every vertex is adjacent to something, right? An important point to note that look at any F, any edge of F, it intersects with every component exactly at one vertex. There is no edge completely contained inside this. That's not how we, because we are looking in G minus F. Okay. So now let's, okay. So this is, let's say, case 1 handled. Okay. What will be the case 2? Every vertex in my graph is adjacent to a vertex in 2 2 and edge in F, right? Because if we had any one of this nature, we know how to handle it. So let's assume that this case does not occur. If this case does not occur, it implies that every vertex is adjacent to, right, to some F edges. If there are some issues, please tell me. Just only keep 3. Okay. Now, what is the situation? Suppose right? Look at him. He could have, he had some neighbors, so here, but look at his, like what I mean by this is, I could also have like this starting from, but look at all others neighbors. So either he adjacent to these people or he adjacent to some people here. Okay. Right? But everybody is also adjacent to some edge in F. What can you say then? If this is how the situation is, what can you say? So what did we learn from this? Can I say something? No. Look, so he had some neighbors here and some neighbors here, right? But whatever it is, right? So if he has neighbor this side, like going outside, then you're counted for, you count them from this. All I'm trying to say this, is this correct or not, right? Because look at a vertex, right? Look at a vertex. He has a neighbor. Look at all his neighbors which are going out. They are counted by this. Look at the neighbors which are inside, right? They are counted by some other f edges. That's all that I'm saying, right? But they all are distinct edges. So what I'm saying to you is that pick up a vertex V. Now it has some f edges which is going out of this component. There are some of his neighbor which is here, right? So these are your f edges which are going out to distinct vertices. Okay. Now look at all these guys, right? These. Now they also have an f edge incident to them, right? But since that there is no f edge in the component, for every vertex is neighbor, the f edge which I associate to are distinct. So it means what I have shown to you is the degree of V is at most f. That's all it is, right? Because like it's like an injection. I have shown to you. Look at the neighbors of V, and I have given you injection to a set of edges in F. That's it, right? There could be many more F edges, but this is true. Now, what do you know then? So, what do you know from here? So, if I delete his neighbors here, as Sanjay was saying, that so what is it? Now, if we delete degree of V, right, then we can definitely separate V from other V. If one like separation, right? But what happens if there is no vertex outside? Like what happens if V union open integer neighborhood of V is equal to Vg? This could happen, no? So if I delete all the neighborhood of V, what are we separating? V is itself. You get my point? Then you have to delete everybody else. But suppose if we deleted DZV and V union N of V is not equal to V, then you have achieved. Why? Because now we have separated a vertex from someone else with size of with a separated of size at most cardinality of F. Because this is why we bounded this. So if I can find a vertex such that which so it was an arbitrary vertex, right? So you find any vertex such that its open neighborhood and itself or its closed neighborhood is not equal to vertex set, then you are great. Okay. So the only situation we cannot handle when a vertex and its open neighborhood put together, that's a V. But this is true of every vertex. Then what graph is this? What graph is this? Okay, excellent. Right. So if what you wrote on this?
Because in this case, we are saying that every vertex is adjacent to n edge on F. So it may not be adjacent to every edge and it may have degree other than n
No.
plus of F.
So look at this. No, here's my vertex. Okay. Where are his edges? Where are its edges? This is a component. Where are its neighbors? You tell me.
Some of the neighbors stand in the component and some, at least one of the neighbors.
Wait. These are some of his neighbors which are going outside. And let's draw all his neighbors which is inside. What are these edges? These are edges of F. Going to different vertex because you have chosen same endpoint. Right? So I have associated different set of edges, say F1, F2, F3. Okay. Now what are you saying? Look at these guys.
Some of them might not be the n plus of F. No,
No,
every neighbor.
this guy has to be neighbor to some edge in F, because that's a true. Otherwise, we are in the case 1. If there exists a vertex which is not adjacent to an F edge,
But case one says that V is adjacent to any edge in F. Oh, are you saying all edges?
suppose there exists a vertex V not adjacent to any edge in F. So what is the contrapposite of this? For all, like all vertex, there exists some edge which is incident to it.
Yeah, some edge, right?
So some edge, there is some edge which is incident to him. Suppose there is no edge incident to this from F, then why am I not in this case? There exists a vertex not adjacent to any edge in F. This vertex is not adjacent to any edge in F. Look, then,
That's why it won't be covered in first.
but this edge is there, no? So that's all that I'm saying. I don't understand your question.
If you remove one of the edge, like from its neighbor.
I'm not removing anything which I do not.
No, I'm saying that one of the black edge is not there from the neighbors of V, then it won't be covered in the first case.
What is the first case?
That there exists some vertex.
The some vertex not adjacent to any F edge.
Yes.
This is it. Any F edge.
Yeah.
Yeah. So if this case does not occur,
This vertex now I'm saying that it is adjacent to
every vertex is adjacent to some F edge. Yeah. So pick up the F edge which this vertex is adjacent to. W1, W2, W3. This is adjacent to some F edge or not? Okay. But can that be F1, F2, F3? Because F1 is governed by something inside and something outside. But if I change inside, whatever may be the outside, that's a different edge. So that's like some F4. Look at V2. Can he be the look the yes, but they are all adjacent to F. No? So yeah, that can be. Yeah, but then wait. Nothing adjacent to F, no? It has nothing, no edge adjacent to F. Then why did I? Then there exists a vertex not adjacent to any edge in F, and let's see the component this, and then I'm done. Right? So so this is, I'm looking, case 2 is a contrapposite, like is a complement of this case, which means for every vertex, some edge in F is adjacent to F. Okay, good. Okay, so case 2 is done if case 2 is done if V union N of V is not equal to V for some vertex V in V, because I pick up that vertex and I separate that from somewhere else, right? But so what are we left with? Left with when for all V, close neighborhood V equal to V. What is this? What is this graph? It's a clique. And in the clique, what is the property? Let's look. In the clique, in the clique graph, we know that kappa G is equal to lambda G equal to minimum degree G. So first you prove this for a complete graph, this is true, and now assume that your graph is never complete, then either of these two cases will handle it. Okay, is that fine? You can just make it single vertex, right? There is no way. Look, for the edges it is clear, right, that I delete lambda minus 1 edges, then I can make him distinct. For the vertex, the only thing which is possible is that we believe that single vertex is both connected and disconnected. Choose anything. based on your need. Otherwise, like, so for this singleton, we assume that, so whenever situation demands you, you can assume connected. Whenever situation demands you that it should be disconnected, then please treat it disconnected. Okay. Okay. So what is this tells us? Lemma 4, 1, okay, it's 1043. I'm really very slow. Okay. So what should I rub? Okay. I can at least start to rub the position statement. So the last thing which I wanted to tell you today is, okay, high connectivity requires what? Large minimum degree, right? So if a graph is highly connected, it implies, because of the previous theorem, the minimum degree is large, because delta G is at least greater than equal to kappa G lambda G, right? So if I say to you the graph is K edge connected, which immediately implies the minimum degree of this graph is at least K. If a graph is lambda, if some K vertex connected, then you know immediately, because of this theorem which we prove, this. But if I tell you the graph is this, does it imply that it is connected? You get my point? So what about converse of this? So like we want to prove a converse of this, okay? It requires large minimum degree. What about, does large minimum degree imply large connectivity? Anybody? Right? This statement doesn't seem to be true, right? So if I look at, so what example could you come up with? Two complete graphs? Excellent. So what Sonak is saying, to take a complete graph on n vertices, pick up one vertex, make it common to, now look at this. What is the minimum degree of this graph? Is at least n. So just so that people, let's say n by 2, n by 2. So the minimum degree is at least n by 2. But how many vertex do I need to disconnect this graph? Just one. Can you come up with some similar example for the edge connectivity? The high minimum degree, but right? So what the chap is suggesting us is that we do this. Look at a complete graph on n by 2 vertices n by 2. Pick up any two vertex and add an edge between them. Right? So again, minimum degree n by 2. This is kappa g 1 lambda g. So in general, this statement is not true. So what will we do? Okay, fine. We give up the hope that whole graph has this property, but maybe there's a sufficient, but does there even a subgraph which has this property? Right? It's a very natural question to ask. Okay, and in this regard, Madder proved a very nice theorem. He said, forget about large minimum degree implying big high connected subgraph. In fact, large average degree implies such a property. Okay. So I want you to tell why most results that you can prove for minimum degree, you can prove for average degree. Okay, and we'll prove the later statement. But let me give you intuition why such things are true first of all. Okay, so let me write down the step. Oh, on purpose I have left this definition. Okay, so that you see it several times. Okay, most modern literature will use this. Okay, so this is a very classic theorem by right. So like Tutt, Madder, Edmonds, like what do you call? There's another person named start from B. Huh? Birch, okay, Thomason, and if you go more modern, right, Seymour, Thomas, right, not Cook, okay, that's computer science, okay. These are the people whose name you will hear more often. Maria Chutkonsky, okay. So when did matter prove this? 1970. So if my understanding is correct, this is not the proof of matter, like theorem is matter, but the proof which is there in the textbook is by someone else later. Every graph with dg at least 2k. So this, what is dg? Remember, average degree. And what is average degree? Just remember, summation of dv divided by total number. So just, okay, sorry, 4k has a k plus 1 connected subgraph H such that, what is this? Vertex right. First of all, it is a k plus 1 connected subgraph H such that vertex per degree is quite large, whatever that means, right? Epsilon H, if you recall correctly, what was that? This is number of edges inside edges of H divided by cardinality of H. This was edges of G divided by cardinality. Just definition one. Okay. So let's ask ourselves question. This is a slightly longer proof. So I don't think I have time to fill the proof, so I will not use it. We'll do it tomorrow morning at 9:30. But my question is, why are we expecting to get rid of min degree with an average degree? We say, look, ideally we would have wanted that if the graph has minimum degree at least 4k, such property holds. Of course, if we prove this lemma, then definitely that's a statement hold, because if a graph has minimum degree 4k, definitely its average degree is more than 4k, right? So this is more relaxed version of the theorem, right? Like, or it's a theorem statement with a weaker assumption, right? Assuming that the graph has minimum degree at least 4k, it's a stronger assumption. Now my question to you is that why these things doesn't matter? Like there's a algorithm to convert min degree to average degree. You understand my point? So for most things you can do that. Okay. So the recipe should be, if a graph has big average degree, what does it imply? Did we prove something? What is the first lemma we proved? Please check, no? Please, has a subgraph with good average degree. Sorry, if we have a graph with good average degree, then there exists a subgraph with good average degree. Sorry, good minimum degree, right? So what should be the first step of our algorithm? We start with good average degree, apply that lemma, get to a good minimum degree, and then proceed. That's it. So is it not like a recipe? So it's like, this is why, like, these lemmas that which I'm trying to teach you are very simple, but they're used as a recipe in very big theorems. So like, how do you get four-phase theorem? Is like, okay, fine, let's apply recipe 1 to give certain structure. Let's apply recipe 2 to give another structure on the recipe, the object which we got after cleaning operation applied by recipe 1, right? So you do these 2-3 steps, and then you get a graph with lots and lots of structural properties, which then allows you to prove whatever you desire. You understand my point? So these are the kind of recipes. So all these are recipe. For some things, this will turn out to be recipe. The lemma, which the Madder's lemma will, because what? So suppose I wanted to prove something about connectivity, right? Starting from average degree. So from average degree, we will go to this, then we will get this. So not only we have a graph with good average degree, and what does this tells you? This tells you, in fact, we have a subgraph which is highly connected and has a good average degree, because average degree or word, they're related with each other. Now we can work on that, no? Right? So if we were talking about proving some properties with some connectivity and something, what will I do? I will start with some basic assumption and apply this lemma or theorem to get a subgraph with all these good properties, and then I will try to prove properties there. Right? So this is why, like, if you know these bricks, you put one by one, and then you try to do your hard work, right? So otherwise we will be like stuck in the beginning itself. Like, it doesn't seem very obvious why such a statement will be true, but like when you put this, oh, the graph is very highly connected. What do you mean high? I mean, I cannot separate this by deleting small number of vertices. It's a big deal, right? Okay. And this proof will use a new proof strategy, and so slightly newer and different proof strategy. So I think it's best that I leave it for tomorrow. Okay? We'll start fresh. Okay, is the speed fine, or should we up it? Should we down it? Let me know at some point. Okay, for this week I will go with the speed, but after that I would like to know your opinion so that we can up the speed. Okay, so here is some task for you people. Okay, just after this proof, the chapter on trees. Have a look. Okay, just have a look. Most things you know, so just have a look so that we don't waste our time on the tree. So to everybody who is listening online, we are largely following this book, Reinhard Astel Graph Theory, and I'm teaching from chapter 1. There is a section on trees, section 1.5 on trees and forests. Have a look at that. There's like most of these things you might know. So I would like you to just have a look at it. There's like 2-3 pages. It's not much, right? 1, 2, 3 pages. That's it. Okay. Just have a look. Okay. Okay. So till you do not have any question, then otherwise I'm done for the day. Why? I don't know, but we can try to prove it. That's a good question. So this is exactly my point. Anything you ask is a question. I don't know. We might have to check this out. Could be. Okay. So when we look at the proof, we'll try to trace it. Okay. Okay. So don't try to do anything. Okay. So we will do this in a collective exercise tomorrow after the proof to trace it out and see where there is a slack in the proof or there is not a slack in the proof, and based on that we'll try to hand construct a family of examples. Okay. So let's do that as an exercise in the class. Okay. I also have never done it, but let's look, because if it is not tight, somewhere in the proof something we should be able to tighten it up, right? Okay. Okay then.